All right, let's dive in. We're going to talk about a battle, a really high-stakes one, that's happening literally all around us, and even inside of us right now. It's the silent, microscopic war between modern medicine and some of the oldest life forms on Earth. This is the antibiotic arms race.
So, here's our game plan. We'll start with the discovery of our so-called miracle weapon. Then we'll get into the nitty-gritty of its takedown strategy. After that, we'll see how the enemy, the bacteria, adapts and fights back. And finally, we'll look at the pretty serious global crisis this has all led to.
Okay, let's set the stage. Every arms race kicks off with some kind of revolutionary new weapon, right? Well, for us, that weapon didn't just change the game of medicine, it completely rewrote the rulebook. So, what exactly is an antibiotic? Well, at its heart, it's basically a weapon from nature's own arsenal. It's a chemical compound that microorganisms, like certain bacteria, say actinomycetes, or different kinds of fungi, produce to kill off their competition. It's microbial warfare, and we figured out how to harness it. Of course, today the term also covers purely synthetic drugs cooked up in a lab, like sulfonamides and quinolones. And this whole thing started, famously, with an accident. Back in 1928, Alexander Fleming comes back from vacation, looks at his culture plates, and sees that some penicillium mold has contaminated one, and it's killing the Staphylococcus aureus bacteria around it. That single observation, plus the incredible work by Florey and Chain to actually purify and mass-produce the stuff, earned them a Nobel Prize in 1945. And it kicked off what we now call the golden age of antibiotics, a period that literally saved millions and millions of lives. So how do these miracle drugs actually get the job done? I mean, to win a fight, you've got to know your strategy. Let's pull back the curtain and see how these things actually defeat bacteria at the molecular level. You know, antibiotics basically have two main playbooks. The first type is called bacteriostatic. These guys don't go for the kill. They just stop the bacteria from growing and multiplying. They kind of just hold them down and let our own immune system come in and clean up the mess. We measure their effectiveness with something called the MIC, or minimum inhibitory concentration. The other type, bactericidal. These are the assassins. They kill the bacteria directly, and their power is measured by the MBC, the minimum bactericidal concentration. Now, the real genius here is something called selective toxicity. These drugs are designed to attack machinery that is unique to bacteria, which is why they don't harm our own cells. And they have some favorite targets. They go after cell wall construction. That's the work of drugs like the beta-lactams and vancomycin. They can jam up the bacteria's protein factories, which is what aminoglycosides, tetracyclines, and macrolides do. They can mess with DNA and RNA synthesis, the specialty of quinolones and rifampicin, or they can sabotage crucial metabolic pathways, like sulfonamides and trimethoprim do. Let's zoom in on the most famous family of them all, the beta-lactams, which includes penicillin. So picture this. A bacterium is building its protective outer wall, which is made of a substance called peptidoglycan. There's a key enzyme on the construction crew called a penicillin binding protein, or PBP, that does the final step. Well, beta-lactams are master impersonators. They look just like the building materials, so they slip into the PBP's active site and just jam it. The whole construction project grinds to a halt. The wall gets weak, and the bacterium basically falls apart. But here's the turn. This is where the arms race really heats up. Because bacteria, they are the ultimate survivors. And for every single weapon we throw at them, they find a way to evolve a countermeasure. And you know what? This wasn't a surprise. The guy who discovered penicillin, Alexander Fleming, he saw this coming from a mile away. In his Nobel Prize lecture way back in 1945, he basically gave this chillingly accurate warning. If you misuse penicillin, if you don't use enough to kill the microbes, you're just teaching them how to beat it. And boy, was he right. So bacteria have come up with this incredible toolkit of defense strategies. First, there's enzymatic inactivation, where they literally produce an enzyme to chew up and destroy the antibiotic. Then there's target modification, where they change the very thing the antibiotic is trying to attack. They can also just block the doors by reducing the permeability of their cell walls. And if all that fails and the antibiotic gets inside, they have efflux pumps, which are like these tiny bouncers that actively grab the drug and throw it back out. Okay, let's go back to our beta-lactam antibiotics for a second. The source of all their power comes from a very specific chemical structure. It's called the beta-lactam ring. You can think of this as the business end of the molecule, the part that actually does the damage. So what did the bacteria do? They engineered a perfect counterweapon. It's an enzyme called beta-lactamase, and its only job is to find that critical beta-lactam ring and break it, turning our powerful penicillin into useless, inactive penicillinoic acid. It's a perfect, elegant example of enzymatic inactivation at work. And that, of course, kicked the arms race up another notch. Our response was to develop something called beta-lactamase inhibitors. Now, molecules like clavulanic acid or tizobactam, they don't actually kill bacteria on their own. Instead, they act like a bodyguard. They basically jump in front of the bullet, sacrificing themselves to disable the bacteria's defensive beta-lactamase enzyme. This clears the way for our original antibiotic to go in and do its job. This all brings us to the really scary part, the spreading threat. Because the problem gets so much bigger when you realize that resistant bacteria don't just pass these survival tricks down to their kids. Oh no, they share them with pretty much everyone. They do this through a wild process called horizontal gene transfer, or HGT. Using these little mobile genetic elements called plasmids and transposons, think of them like tiny USB drives full of cheat codes. Bacteria can pass their resistance genes to totally unrelated neighbors. They can do it through conjugation, which is direct cell-to-cell contact, transduction, where a virus acts as a delivery service, or transformation, where they just slurp up free-floating DNA from their environment. And because they can share these plans so fast, we've seen the rise of so-called superbugs with some truly terrifying abilities. We've had to create new categories for them. It starts with MDR, or multi-drug resistant, and it goes all the way up to PDR, pan-drug resistant. And pan-drug resistant means exactly what it sounds like. It's resistant to every single antibiotic we have. And this isn't just a problem that's stuck inside hospitals. It's a single, massive, interconnected crisis. There's a concept for this called One Health. It recognizes that these resistance genes are moving freely between people, farm animals, and the general environment, through our soil and our water. So a resistance problem that starts in one area will inevitably become a problem for everyone else. Because the threat is so real, global health organizations now keep what are basically most wanted lists of priority pathogens. The critical list is the stuff of nightmares. It includes things like carbapenem-resistant Acinetobacter baumannii, Pseudomonas aeruginosa, and Bacteriaceae. These are the superbugs where our treatment options have dwindled down to almost nothing. So when you put it all together, you realize this isn't some abstract problem for the future. It's an active arms race with real life and death stakes, and it's happening right now. Which really just leaves us with one pretty sobering question to think about. Are we actually running out of time?